Hi, I'm Josh.
I'm Jeremy.
And I'm Nick, and this is our Dexterous Manipulator.
In industry, there are many situations that are considered dirty, dull, or dangerous, that are unsuitable for completion directly by humans.
Enter our Dexterous Manipulator system. Our robot enables humans to be physically separated from these environments. It enables the operator to control the robot in such a way that it mimics the operator's arm movements, enabling a very natural feeling control system.
Here we see a potential use case of our system. In front of the robot is a hazardous material that a human could only move if they were wearing full personal protective equipment. Our robot allows the user to remotely move and manipulate these materials, keeping the user well out of harm's way.
Handling volatile and dangerous substances is just one use for our robot. It is also suitable for use in environments inaccessible for humans, such as deep-sea exploration and even remote manipulation in outer space. Our original goal was to build a robot arm with 5 degrees of freedom that could be controlled by an imitative controller. This formed the basis of our requirements, however, we managed to go beyond our base goal to create a dual-armed Dexterous Manipulator system that had 5 degrees of freedom per arm, as well as an additional 6 degree of freedom that is shared by both arms. So what's so special about our robot? Let's take a look.
It has an operational radius of 1.1 meters and is capable of lifting 1 kilograms per arm. It can be controlled remotely by a controller such that it mimics the operator's movements.
Our robot has 2 arms that can perform actions simultaneously. It has 5 degrees of freedom per arm and 1 shared that allowed for truly dexterous manipulation.
It is compatible with a standard 12-volt car battery as a power source, and it runs on 4 Cypress PSOC 5LPs.
Now that you know a little bit about it, let's take a look at how it's constructed.
There are 4 types of materials that we used in this project. 3D printed material, aluminium, steel, and acrylic.
3D printing was a strong tool that allowed us to prototype and iteratively design our joints, improving upon errors or oversights. All printing was done using ABS filament with the printing specifications of 80% fill and 6-layered walls. This is to ensure durability, allowing our Dexterous Manipulator to carry heavy loads. Aluminium was used to construct the frame of the robot, such as the torso and arms. On top of that, high tensile steel shafts were used for the shoulder and twisting joints. Steel, being much stronger than aluminium, was chosen as these shafts experience high torsion force due to the weight of the arm. All aluminium and steel parts were machined at the ECSE department's mechanical workshop. Finally, acrylic was used quite substantially in our project as it was quick to manufacture. What may take hours to manufacture in a machine shop may only take minutes to be laser cut in the CAD/CAM center. Each part of the robot was carefully modeled on SolidWorks to ensure not only the feasibility but the scale of the robot before manufacturing. Many motors were used in the construction of the robot, each chosen according to its speed and amount of torque needed to move the specific joint. The torso was designed into 2 separate parts, the upper torso and lower torso, allowing the robot to lean forward. The frame was manufactured using 6mm aluminum sheets, assembled together using multiple screws along the edges. The torso's extending mechanism is driven by a linear actuator sitting inside the torso, which is rated to lift a load up to 90 kilograms, which made it perfect to be used for this purpose.
Atop the torso, we mounted a platform for each arm's shoulder to attach to. The shoulder consisted of 2 degrees of freedom, rotation and elevation. For the rotation of the shoulder, we used these motors. They came with quadrature encoders already mounted, which are used to track its motion. Additionally, we mounted a limit switch to the shoulder platforms to home with upon startup. For the elevation, we used the same linear actuators as the torso. Their power is adequate to lift the weight of the arm and any load it is carrying. Their inbuilt limit switches meant no additional switches needed to be incorporated. However, it meant we could not utilize them to home with. Hence we required a form of absolute position encoding to track the elevation, so we utilised a 10 kilo-ohm potentiometer for this purpose. Attached to the shoulder joint is a twisting joint responsible for rotation of the elbow. Our choice of motor had to provide large amounts of torque to be able to lift the lower segments of our arm. This motor had a gear ratio of 630 to 1 and could deliver 80 kg-centimeters of torque. Preliminary tests indicated that this to be sufficient in lifting the weight of the arm. Special brackets were formulated to adapt this motor's off-axis shaft to be centered within some aluminium tubing. Using some shafts and couplers, it was secured to the rest of the arm. Mounted quadrature encoders enabled position tracking, and to home this joint we made use of small Hall effect sensors and small neodymium magnets.
The elbow joint was designed with the intention of keeping the mechanics as hidden as possible. To this end, a self-made linear actuator was built to be completely concealed within the arm. The high-powered motor within extends the actuator, which in turn extends the lower arm, and retracts in the same way.
Attached to the elbow was the lower twisting joint. Whilst mechanically the same, unlike the upper twisting joint, it did not require tracking as it was user actuated. The motors had no encoders and a gear ratio of only 100 to 1, delivering 50 kg-centimeters of torque. To track limits of rotation, Hall effect sensors in conjunction with neodymium magnets were employed.
The gripper was designed to be screw actuated, consisting of a threaded shaft coupled to a brass block. As the shaft rotates, the block moves up or down the shaft, opening or closing the gripper. This shaft is driven by a small high-speed motor, allowing the gripper to be opened and closed quickly. The brackets holding the motor and gripper in place were 3D printed, whilst the linkages of the gripper were made using acrylic to reduce the weight of the arm.
Our imitative controller required only 4 degrees of freedom: shoulder elevation and rotation, upper arm twisting, and elbow extension and retraction. Using some Omron quadrature encoders, brackets were devised to mount these encoders to track these degrees of freedom. Each controller arm was mounted to a shoulder platform where circuitry was housed and had a gripper handle at its end that housed buttons to control gripper articulation, state transitions, and torso tilt.
As part of the robot design process, we designed and had manufactured custom printed circuit boards, or PCBs. Together with the PSOC microcontrollers, these would function as the brains of the robot, connecting sensors to actuators with C-code defining the interaction between them. We required 2 PCBs for our robot, one on the robot itself, in charge of connecting the robot PSOCs to the actuating motors and sensors, as well as another PCB on the controller, connecting the optical encoders and controller buttons on the controller arms. Both PCBs primarily exist to simplify the input-output to these external components and the PSOCs. Both boards also include a 12V to 5V DC to DC converter circuit. The biggest advantage of including the PCBs in our design was clearing up the mess of jumper cables present in our breadboard implementation of the robot's circuitry. We spent considerable time and effort to route wiring neatly, color-coding any wires for their designated purpose. This made the connections between components much more secure and made the robot look more professional and presentable. The biggest disadvantage of opting for custom circuit boards was the time taken to complete them. Altium, the software used to create the PCBs, had a steep learning curve as it was not taught in any units we studied. Learning Altium, designing a PCB, and iteratively improving it took most of the second semester. The PCBs were made by PCBWay.com, a reputable PCB manufacturer in China. The sensors and actuators were connected to the PCBs primarily through the use of PCB mount screw terminals, while communications between the PCBs and H-bridge array was implemented using IDC connectors. Communication between the two boards was implemented using Cat5e cabling terminated with RJ45 connectors. This was chosen as it is an industry standard for communications with readily available components. The Cat5e cabling contained 4 twisted pairs of wires, with 4 wires in use for serial communications and the remaining 4 split evenly between connecting ground and carrying 12V power for the controller. The true brains of the robot are the 4 Cypress PSOC 5LP microcontrollers split between the controller and robot. Initially, we considered running the robot off of a single more powerful controller, such as a Raspberry Pi, but opted instead for an array of Cypress PSOCs as these allowed us to program digital logic on the same boards.
Our controller and robot communicated to one another over a wide SPI, or Serial Peripheral Interface, connection. The controller sent a continuous stream of data indicating encoder positions and button states using 9 bytes in each instance. The data link operated at a rate of 5 kilobits per second, which saw a conveyance of controller state at roughly 70 Hz to the robot. Instead of using the CPU to handle this serial communication channel, we employed DMA, or Direct Memory Access, modules to allow CPU time to be devoted to our control algorithms. The DMA would copy data from SPI buffers straight to memory where our control algorithm could access the data. Included in this data is an indication of whether the system is in calibration, paused, operational, or shutdown mode. Using buttons on the controller, this mode can be changed. When the state button is pressed, the robot cycles between calibration, paused, and shutdown. In these modes, the aims move to preset positions for their namesake. Calibration moves to a position with which the controller and robot can be synchronized, shutdown moves to a transportable position, and paused holds its previous position without moving. If a trigger is held whilst paused, the system moves to operational mode where the arms imitate the controller. Our control algorithm consists of 4 discretized PID implementations. Given an error signal between robot and controller positions, these algorithms act to minimize the error by adjusting the speed and direction of each imitation joint. It does so by adjusting the duty cycle of the PWM modules which are driving each motor. Varying the duty cycle controls the power that the motors are exposed to and consequently their speed. This algorithm is driven by a timer-based interrupt at the frequency of the PWM modules at roughly 4 kHz.
Innovation never stops. There are always things that can be improved upon. For our Dexterous Manipulator, one of our limitations is the range of motion. The elbow, due to the lack of space in the arm, only allows for a range of motion of about 80 degrees. This could be improved by using a smaller inline actuator that has a longer stroke length. Moreover, by lowering the position of the linear actuator in the shoulder joint, its elevation could be improved to allow the arms to be raised higher. External wiring limits the twisting joint motions to around 180 degrees. This could potentially be solved by implementing slip rings which will allow all twisting joints to rotate freely without any limitations. Another improvement could be the addition of a gimbal joint onto the end of the gripper. This would allow it to flex in a similar way to a human wrist, giving that extra degree of freedom at the most important joint for manipulation. Our biggest challenge in designing the robot was the limitations in motor strength due to the weight of the arms, in specific, the upper twisting joint. This can be improved by getting better motors, or even scouting out lighter materials while still preserving the robustness of the robot.
Due to time constraints, we were forced to limit the scope of our project to what we have shown so far. Some of the features we wished to implement included a first-person camera system to provide feedback on the arm's operations, wireless communication, especially if the base was to be mobile, and programmable positions or motions of the arm. The biggest addition would be the inclusion of a mobile base for the manipulator to rest upon so that the whole system could be made mobile. This could be extended to include a backpack mountable controller, enabling the entire system to be made portable.
Thank you for watching our video. I hope it was very informative.